Howdy tubers, welcome back to the TZL Scada part 3. So this video is going to be mostly about this circuit board. Before I get rolling on this, I would like to say that this project has probably been one of the most challenging projects that I've ever done. I have had bigger projects, but it has been one that has required me to develop numerous new skill sets, things that I had never thought I would need. I've got a pretty good understanding of electronic components, but I never thought I'd have to design a circuit board. And this is exactly one of those sets of skill sets that I've had to learn. I went through several different renditions of this. I started off with a hand soldered homemade breadboard type system. And then this is the third one that I've actually had manufactured. The second one was closed, it had a few issues, but anyway. This board is going to work in junction with a lab jack. We've already talked about these lab jacks. This is a digital analog converter. This allows a computer through a network or a set of radios and stuff to communicate from this back to a computer, where the computer can read the registers in here and see the different input voltages. It can turn on and off output controls, whatever. This is what allows the computer to, the first step for the computer to be able to communicate with our SCADA system we're putting together. This has got some limitations, and this is what this board does, is it allows us in the specific things that we want to do, it allows this lab jack to do them. And to get in real quickly, this is controlled. I got one put together here. We've got to take the lab jack apart, and I'll show you all this in a minute. We put some parts on the lab jack, and the lab jack and this board actually snap together. They go in a box. I'm going to show you the box later. But this thing does a numerous set of things. The first thing it does, it's got a 24-volt input from a wall wart, and you plug in the wall, so it powers it. And it powers everything. We've got a set of batteries, and there's a guy, several comments, people asking, I had a whole bunch of batteries over there on the wall. Everybody says, what the heck is that? Well, it's for the SCADA system. And so this has the ability to use the battery backup to power everything. It can charge and maintain the batteries. If you use the battery backup and they go dead, this obviously recharges the batteries. It's also got, from the 24-volt input, it's got a voltage step down. This allows the lab jack and all the 0 to 5 volt sensors to run off this as well. It's got several different filter capacitors to filter the signals and stuff coming into it. It has got, like I said, a system to switch between the battery backup and the 24 volts. It allows the lab jack to be able to tell through an input whether it's running off batteries or it's running off AC. It has got some USB outputs. You can plug a USB powered YZ camera or something into it. It's got some relay outputs. These are 5-volt rated relays. And so this allows the lab jack to be able to control higher voltages and higher currents than it ever possibly could. These are, I think they were 200-volt rated relays. We just got common in and out through the relays. But I'll probably limit it to 24 volts, but this allows to run like an ice cube relay or something to turn something on or something off. It's also got overcurrent protection. If we've got a short in one of our sensors, it doesn't just blow everything up. There's there's 4 sets of self-resetting thermal fuses, and there is also a set on the input to the charge circuit. Everything here has got self-resetting fuses. If you short anything out, we shouldn't be able to blow anything up. The last thing here is we've got a power over Ethernet injector. I'm not going to get into this in this video, but I'm using these type radios for the lab jack to be able to communicate back to my network. And these radios use a real simple power over Ethernet injector. And the problem with this is if you've got this running off 120 and the power goes off, well, the radio doesn't work. One of the most important things, probably the most important thing that I wanted to be able to monitor with this system, is whether or not my water pumps have got a power failure, whether electricity has went off for one reason or another. And if your radio goes dead, obviously you can't do that. And so these use If we've got a power over Ethernet injector made into it, we'll just have a Ethernet cable that plugs from here into the radio, and these will self-power the radio. And if electricity goes off, of course these go immediately to battery backup. In fact, they don't even go off, it'll do it instantly. And the lab jack through this relay and some other stuff can tell that the device is now running on batteries, and my computer can send me a text message and say, hey, so-and-so lease has no electricity. So we've got several parts to put on this, but I want to give you an idea of kind of what's going on. I might talk a little bit more about it later, but let's come over here. We got to disassemble the lab jack, put some parts on the lab jack, and there are a few parts that we need to put on the board. All right, let's build this board real quickly. There's a few components we got to put on here. This board was made by PCBWay for me. It is completely custom. I designed this. I'll show you a little bit of the program that we use in a minute. But there's a few parts to put on here. The first is these little screw down terminals. I had a little bit of trouble in the language barrier explaining them what I wanted here, and so basically just gave up, decided to put it on myself. And then also there was a few other components. Basically we've got two more that are relatively complex. This is a step down and this is a step up. Let's get these put together and soldered on here, and then I'm going to go over in detail on this board exactly what everything does and may show you the schematic. All right, I got both of these screw terminals tacked down. Let's solder them down real quick. Okay, so to use this, we've got to take it apart. And we've got to remove this plug. We're not going to resolder into the holes, but it's covering up these holes here on the end that we're going to solder into. I tried to desolder a bunch of these and I found it's easier. We can just sort of bend this plug up and the plug sort of comes apart. Be careful not to tear up anything. When we go in here and real carefully, without scratching the board too bad, we'll just go here and cut all of these. All these off here. We'll go and cut these little mechanical straps. I don't know what you call these here on these metal things. And we've got to make sure not damage any components on the board. It's easier to do than you would think by getting in it with a wire cutters. Just like that. So the next thing is we've got to solder. You'll see what these do in a minute, but these are little things that receive the pins. We've got to solder these on right here. We've got 3 of these. They go on here. They go just like this. And I'm going to flip this over. We're going to take some solder paste and blob a bunch on here. Remember, we're putting connectors on, not processors. Yeah, my fan speed too high, blew it out of the way. Okay, so what exactly am I accomplishing with this board? When I set out to design this, it had a lot of things it needed to do. We've kind of hit on that. We'll talk about it more in detail in a second. But we needed the battery backup. I wanted some, USB power ports. We had to take the 4 to 20 milliamp sensors and change that input over to where this could read it as a voltage. And that's what this board is doing. Now, as far as the lab jack goes, the changes we have made to it, we've simply, by installing these connectors, this is just simply another way for the lab jack to read something without having to use these screw terminals. I didn't want, a bunch of wires lapped around or whatever. And the lab jack conveniently comes with these vias laid out in a way that you can put a you can put a plug in here, and this is a standard plug layout. And so basically all these is a way to have an input into this thing without having to use the factory, the factory wires here. We can have this all grouped together, and that's exactly what this does. These two boards actually just pin together. It's a little bit of a trick. See if I can do it here on camera. They just pin together, and now the inputs to this board go through the board and then read through these 4 pins here, 8 pins and 4 and 4 up into where this can read it. Okay, so let's go over this board and everything it does. First off, we've got a power input. I have got a 24 volt transformer wall wart. This isn't really a wall wart, whatever you'd call it. Power supply. Those are cheap from Amazon. It simply plugs in, and this powers everything. This is, I'm going to use the word power inclusive, meaning that I wanted everything in this whole system to be powered by this. So the radios, your IP cameras, the sensors, everything. And so if this goes down, we've got a battery backup, and the battery backup can also power everything. I wanted it to run the cameras. I wanted to do everything. I didn't want to have, if the power goes out, I didn't want to have any loss of usability of this system. So we've got 24 volts comes in, it goes through a relay. The coil of this relay is powered by the input. So when you power this, send power to here, it closes the relay. The contacts in this relay carry power on to the 24 volt system of this. So I missed an additional point here. This relay has got an additional set of contacts in it that are used back through the expansion port plug in the lab jack, and we'll talk about in a minute, so that the lab jack can tell whether or not this relay is open or closed, and therefore can tell if the system is running off batteries or if it's running off a power supply. It goes through and powers the power over Ethernet injectors at 24 volt DC. This one has got the pins that carry the Ethernet part on to the LAN output, and this would be a power over Ethernet. This would be power over Ethernet, like set 1, set 2. And then anyway, the 24 volts is connected to the correct pins to power the relays. So the 24 volt comes along, it goes over here, let's see, to our 4 to 20 milliamps. The 4 to 20 milliamp sensors run off nominally 24 volts. There is a right here a self-resetting thermal fuse. This is a thermistor. If this gets hot, it kills the power going to the sensor. So if something shorts out, this works just like a self-resetting thermal fuse. It will trip, and then if you unplug it or just fix the issue, it will cool off and reset. There's several of these. This one is the 24 volts to the sensors. This is the 5 volts to the sensors, and this one is actually used in the charge circuit. I'll talk about this in a second. The 4 to 20 milliamp sensors come back in here. We've got 4 thermal fuses. If any of the sensors short, this will limit the current that's available inside the tank, hopefully low enough that you can't create a spark. It limits them to about 40 milliamps. We've got a set of small resistors. These resistors are what changes the current to a voltage. We talked about that in the first video. Anyway, these are then carried via the other side of the board through some vias and back through these 4 pins, and these 4 pins are what connects back to the lab jack. The 0 to 5 volt stuff is similar. We're sending 2 ground wires and 2 5-volt positives out. The sensors come back and they connect directly to these. Also, these 4 to 20 milliamp sensors use one of these 4 capacitors, and these capacitors are simply a filtering capacitor. The 4 to 20 milliamps seem to have some relatively high-speed noise in it that the capacitors more than take care of that. Anyway, 24 volts comes up to this. This is a voltage booster. This takes 24 volts up to 28, and this is what is used to charge. You can actually adjust your charge voltage via this little multi-turn pot, but this is what is used to charge through. It goes to this self-resetting fuse at 100 milliamps. Out through here, it charges the battery. These little self-resetting fuses, there's nothing that goes bad in them. They simply get hot. When they get hot, they have a higher internal resistance, and so this works really less like a fuse and more like a current limiter. And so this limits the charge current to, in real life, around 50 milliamps until it gets up to close to being charged, and then they'll close and actually charge a little bit higher a little higher current as the battery gets close to being charged, and bring them up to full charge voltage. These boost boards, I had a problem with this little chip blowing up, and so the power from the 24 volts into these actually goes through a filter capacitor and a 1 ohm resistor. And for some reason, you know, these have obviously got capacitors in them, they're charged up. When you would plug this in, about once out of every 50 plug-ins, this chip would pop. And it just had to have something to do with it's, I don't know, it's charging the choke or something. I really don't know what. But for whatever reason, these blew up, and they required a 1 ohm resistor and a filter capacitor on their input side. Okay, let's talk about these 8 pins here at the bottom. So we put this plug on the lab jack. This is where these pins plug into, and this is basically taking the place. We had to remove this plug. This is taking place of this plug. Now the lab jack has got, you can buy a expansion module, and that's basically what I'm using here is this expansion module plug. Obviously the plug's gone. But what these are is you have got several different, there's a couple of analog, but most of them are digital only inputs and outputs. A digital output would be a switch that you could turn off and on. One of the problems here though is the output of these is directly controlled by the microprocessor, and this processor probably has a maximum current of only a few billionths of an amp. And so what we had to do here is we have taken a couple of really small transistors, relay drivers. We've got a flyback diode, so when the relay goes off it doesn't blow this up, and we've got a couple of resistors that limit the current coming from the lab jack into these transistors, and these are really small. I don't know how well they come through on camera, but basically these are used like an amplifier. And so we've got a little bitty tiny current that comes from this microprocessor through these pins, and this amplifies the current, and this allows the current to go down here and turn off and on these couple of relays. And so we've got 2 outputs here controlled by the lab jack through these relays that are right here. We've got the contacts of one relay and the contacts of the other relay. What this allows us to do is to control something relatively high power, you know, we're talking about 5 amps here, by the lab jack. And obviously you can step these out into your control panel, and if you need to actually control something large, you know, you can run a 12 volt signal or 24 volt or whatever through these relays to control a large relay or a contactor, you know, if you need to control a, you know, unlimited size motor. The other 2 things we've got here is we've got 2 more relays, and these are inputs. And so while this is powered up, if we short between the common, which is a ground, this one, and this one is just a ground here. But if we short either of these 2 to ground, we're going to close the circuit on the coil of these relays, and this is the input to this board. And when these relays are closed, it actually shorts a couple of these pins to ground, and we'll use that as a digital input. The lab jack can then see that one of these has been pulled to 0, pulled to ground, and it will show a low voltage. And so we can use these, as I say, as an input to read whether it pumps on, or, you know, a contactor, you know, do whatever, you know, anything you can dream of. So that's about the size of this. You know, electronics like this are not hard to design, but sometimes they're hard to get right. I made several mistakes and had this made. This is the third one, and it took me a couple tries to get everything exactly like I wanted it. So I want to show you real quickly, this is the program I used to design this circuit board. It's called KiCad, K-I-C-A-D. It's got this part here, the PCB editor, where you lay out all your components, whatnot, and then it's got a schematic, sort of half of it. You lay out your schematic, the components that you need, how they're wired together and whatnot. And when you come over here, it actually helps you. It tells you if something's not wired correctly. It helps you lay all this stuff out. You put everything where it needs to go, and then design your tracks and whatnot. It's also got a plug-in PCBWay. You can use that as a really easy way to communicate with PCBWay's website, and they're the company that actually manufactured these things for me. This is the next evening. So I got the voltage set on the charge voltage on this voltage booster. Basically, just put a voltmeter on the battery terminals here, and you adjust this little pot till you get it to about 27.7 or 27.9, something like that. You just line these pins up, and this thing snaps down on there, just like so. So I'm going to haul this over and plug it in the computer, and we'll play with it some more. So here is what we just put together, and here is what it looked like once it goes in the case that I built. It's upside down right now, but both of these layers go in here, and it's a quite crude but useful mounting hardware. I made this on a 3D printer. That was quite an extreme learning curve. It's not something I want to spend any time on. If you want to learn how to make something like this, there are much better videos out on YouTube that I will never be able to put out. For what it's worth, the program I use is called FreeCAD, and I forgot what the slicer. Anyway, you can learn somewhere else how to do that. But this is what this will look like. It'll be powered. See, I've got a long USB cord here. It'll have a much shorter one, but this is powered from one of these USB ports. And then this is a power Ethernet injector. On the next video, we're going to talk about the radios and stuff I'm going to use, and the networking, and very few detail. I don't want to get too lost in that because it's not something I'm good at, but I want to show you sort of what was hard for me and what I learned. But anyway, from here you would have your radio up on the pole or whatever. Now, we don't have a radio hooked up to this, and this will run off directly through a USB. So we're just going to plug this directly into my computer, and we can link up. We can link up right here with the LabJack Kipling. So this is what that board is supposed to look like. I think y'all probably seen it by now, but I've just taken the plastic off of all of them. So anyway, we have got here a different set of inputs and outputs, and we're going to use these as analog inputs. There is some phantom voltages here because we're using two different. It's being powered from this plus a ground to the computer. It kind of jacks some of this. And then we've also got here this bottom plug is a plug that we cut off that was down here, and we're using 8 of those of these pins are going through to this other board. And so there are 2 of these. I don't know if you'll be able to hear it. We want to use output, excuse me. These are the 2 relays you can hear. We can turn those relays off and on. And that is 2 of these, and this would be like this relay or this relay. So if we have something in circuit here, we can have the ability to turn it off and on. So I've got a couple of quick points I want to make here. I am doing my best to make these videos understandable to someone like me as I was a couple of years ago. And you know, this is not what I'm naturally good at. Obviously I've figured it out now. I can do the electronic kind of component stuff, but I'm not good with computer stuff at all. It's just too abstract. It doesn't work well with my brain. Anyway, I'm trying to take these through a sort of natural progression, if you would. You need to know this, to know this, to know this, to know that. But I feel like I need to, this is one of the times I need to sort of back up and tell you what's coming on down the future, down the line, to make it a little bit easier to understand what we're dealing with right here, right now. So the program we're using here is called LabJack Kipling. And it is a very simple program that, again, it gives you a visual representation of what's going on with the LabJack. And it is a quite useful tool even in the field as you set these up. You just plug a computer into it, they link right up. You can kind of see, give you an idea of what's going on. But it is not a SCADA software. It's a configuration software and a basic see what's going on type software. The SCADA system software that I purchased is, the name slips my mind, I can't think of it. But it's a very sophisticated software that'll do more than I could ever imagine. It's way outside my ability that I'll ever have as far as script writing and stuff like that. It'll do anything you can dream of. But I wanted to talk about the way it communicates to this, and just to let you know that basically this program isn't the end program. We're not going to get on here and look at a little visual representation of the LabJack to see if I got a water pump running or not. But this will be given an IP address in my network, and that SCADA system software will know what the IP address of whatever LabJack it's looking for, whatever lease, what that address is. And so it'll yell through the network, hey, IP address to LabJack, lease X, whatever. I need to, and it's going to request a piece of information. And all the information in this is stored in what's called a register, or registers. And there's just a book basically on the Kipling you look up, and it tells you which one of these or whatever is what register and what communication protocol it uses. So anyway, I believe 1012 is the one that's been being used for the whether or not the water pump is running or not. And so basically the computer and the software in my office is going to yell through the network, hey, IP address, blah, blah, blah. We want to look at register 1012. Well, the LabJack receives that request and then sends back through the network to the computer the answer to that question. And it's either going to say the water pump is on or the water pump is off. And then once that's in that other program, that program can digest and do whatever you want to do with all the information this is given, and graph it and run it through scripts and decide if there's a problem or whatnot. Anyway, I wanted to kind of tell you the next step of this, if you would, so we can better understand kind of what we're looking at on this Kipling program. Now the other thing here is these other two relays we should be able to trip, as you can see, 1 and 2. And I'm going to have a hard time holding the camera and showing you this all at the same time, but if you notice, I think this will be one of them. If I short these two pins together, and this would be like the water pump comes on, it'll show it. Before in this video, I got one more point I need to make here. There are two RJ45 jacks on this that are normal Ethernet plugs. There's nothing special about them, but they are not networking plugs. They're not set up to have any kind of networking stuff ran through them. It's just a cheap, normal, easy to come by jack that has normal, easy to come by cable, Cat5, with normal, easy to come by ends, that allows me an easy way to connect sensors to this board. Now there are two of these. This one will have this will be the input to the sensors that are 4 to 20 milliamp, and this one will be the ones at 0 to 5 volts, basically pressure and tank level. And if we can do anything we want with these wires, we can short any of these together. Everything's internally protected. We don't have to worry about hurting anything, but we should be able to short a couple of these wires together and see it on here on this. In fact, I've actually, hold on, I'm gonna hook up a sensor. I got a sensor right here. Well, I'll pick out which one of these wires need to be used and we'll play with it. Okay, I've got the pin out figured out on this. Obviously when I put these in, I'm gonna have a standardized pin out, but it's not the same as Cat5. So if we look at this bottom number here, when I hook this sensor up, it should go to about 0.4, as it does. Now if I blow on this sensor, the number should go up, as it does. I just kind of wanted to show again that this is sort of taking the place of the couple of resistors and a bunch of wire that we had wrapped around everywhere in the first video. But anyway, I will be able just to come out of this device with a single Cat5 cable, go up on top of my tank batteries, and then just break out each sensor. Now coming the other way, this will be the 0 to 5 volts, which is the pressure sensor, will go the other way, and it'll go by the separators and the water pump and whatnot. I just want to make this clear that this is how the sensors will connect to these, is through these two Ethernet jacks. So I want to do a quick demonstration of how sensitive these sensors are. You know, this thing has got, it's an old, I think it's an old Gatorade bottle I found, a glass bottle. It's got about 1.5 inches of water in it, I would guess that is. Here we're measuring 0.43 volts, 0.403. We drop the sensor in there, it comes all the way up to 0.417. There's a significant readable difference simply in that 1.5 inches or 2 inches of water. Okay, so this is the end of part 3. I felt like that these videos, these couple of parts of videos sort of went together, and that's why I released them together. Here in a couple of weeks, I'm going to have another group of them out. We're going to do, you know, this was sort of a inside videos. The next is going to switch gears a little bit. We're going to leave this actual data acquisition system alone for a short period of time. The next videos are going to be about the networking. I am not a network computer guy, and nothing I hate more than people that put YouTube videos out that don't know what they're talking about. But I'm going to give you a rough overview of sort of what I've got, at least the components that I'm using. And then we're going to go kind of backwards a little bit into my camera systems. I want to talk about the cameras that I'm using. It's all cheap stuff. And we're going to talk about the actual shutdown systems. Also, there's going to be a video, if this works out like I think it will. I've had a lot of trouble with lightning, and I'd like to incorporate in the last one of those kind of what I'm doing to help lightning suppression. And I would like to get a lot more nitty-gritty into the details of what's going on. There's a whole lot more to it than meets the eye. And I've had some good suggestions, and I felt like that I might have led y'all astray a little bit in the issues that we're having. And I'm hoping that if I give y'all some better information, I might come up with some better ideas about the lightning problem that I have. Anyway, networking, cameras, shutdown systems, and then the lightning problem. And then after that, we're going to pick this stuff back up. We're going to go out and do another group of videos. We'll install this, and then we've got a lot of programming to do in the computers and that kind of stuff. And we will wrap up the SCADA system. I appreciate you watching. There is a playlist. If you get lost, it'll be in order. Click on it, the link, when I get all these up. When you watch this, it might not be there, but shortly after, if you see this at a later date, I'll have the playlist all straightened out and everything. Appreciate you watching. Catch you on the next one.